Okay, so I'm going to go ahead and get started. I'm excited today because we have a couple of presenters that are going to be presenting two different tools. First, we have Tomasz Ostrachil, who's going to be presenting a tutorial on QuickFit. And Tomasz is a general atomic scientist. He's been here 7 years and developing in a variety of tools, Infrared, QuickFit, PyTomo, as well as kinetic fit time, Neo, T-Gyro, et cetera. So he's got pretty wide experience with a variety of tools. So he should be fairly knowledgeable about what he's going to talk about today. And then he specializes in particle and purity transport. So if you have any questions on that, feel free to ask him. And then the other topic we're going to have today is kinetic fit time. And I'm excited about that. Brian Victor is going to be talking about that. He's a Lawrence Livermore National Lab scientist. He deals with steady state and advanced tokamak scenarios. And he's been, one of the aspects that he brings to it is he's a user of kinetic fit time, a really strong user. And so he'll definitely give you a perspective from that perspective. So anyway, with that, I'm going to give the floor to Tomasz.
For the introduction, it will be a short tutorial because we will be followed by a larger and more important module, but this one is certainly very interesting. So I will start with importing of the module. It's called QuickFit. Now it's first open, and in the last tutorial you have learned something about OMFit profiles. So the purpose of this tool is similar, but it has a very different philosophy. OMFit profiles were originally built for fitting of single time slices one by one. The QuickFit is from the beginning built for the fitting of the time evolving data, do a two-dimensional fit, not just in the radius, but also in time. So it's using 2D Gaussian processes to perform a really fast and highly accurate estimate fits of the data. And it's using this, taking this advantage of the 2D approach in every single step to make it really fast. So first you will select a discharge. I will use a standard discharge used in many other tutorials, 163 COC. You can select the eFit edition. It lists all eFits which are available in MTS Plus. So you can go and select, for example, Cake 01 edition. Then in this panel, you will select a kinetic profile which will be fitted, and select the details, which system is loaded if you want to use tangential CR system for ion temperature or also vertical data. But by default, just keep it as it is, unless you have some special constraints, you are missing data, keep the default values and select the time range. I will fit the entire discharge from 1 second to 6.4 seconds. That's a time range where the equilibrium is available. The step, you can use a finer step for the time grid, but by default, it will use the time step of the diagnostic. So if it, in case of CR, it's usually about 5 milliseconds. So raw data is done. And you can look on the ion temperature profile. It's really fast, so you can use it also in between the discharges. It supports, it can load the data from multiple different flavors of CR analysis, so you can use even the real-time analysis and look on the CR data just immediately after the discharge. This slider is used to move in the time, and now the most important part is the fitting. Just press the button, wait a few seconds, it's done. It has fitted the whole discharge from the beginning to the end, and in fairly good quality. So what are the other sliders below? The first slider is used for the changing of the temporal correlation length, and the second small slider is for the changing of the radial correlation length. So if you want a very smooth profile, or you have, by default, it's trying to estimate this correlation length by internally, but the user can define what he needs. If he needs, if he prefers to have a small time resolution but very fine gradients, you can reduce the time resolution, will not really change the fit significantly, or you can increase the smoothing, the radial smoothing, and refit it. If you see the line is flatter, or you can follow every single bump in the data by reducing the radial smoothing. But most of the time, the default value works fine. So yeah, another issue with the experimental data, there are often some outliers. In this chart, there are not, but if you have the outliers, you can follow the simple help, which is below, by selecting, using the left mouse button, select the point which you want to remove, or right mouse button, and you can undelete the points. Or if you will press the control, this is removing only the data in a single time slice. But if you want to remove these channels for the whole discharge, just press control, select the data, and it will be removed for the entire discharge from the beginning to the end. So it's really helpful if you have corrupted channels. Yes.
Going back to the radial smoothing, is there an option to have one value for the pedestal and a separate one for the core?
It's using a different value for the pedestal but you cannot separate it. So it is using different value for the pedestal and core, and this is just rescaling both values by the same number.
Okay.
Question? Yes.
What makes the fetching so fast? I feel like in OMFIT profiles, it would still
what makes the fetching in OMFIT profile so slow? I don't know. Yeah, I done just carefully. You need to fetch only the data which are actually needed.
My perspective, I think OMFIT profiles loads a lot more data than Tomaj needs. And I think that's why with OMFIT profiles, you often end up with bigger project sizes than you do when you're using QuickFit.
Okay. Basically, you can have also huge projects because you are fitting every hundreds of time slices, so it can be large. Yes, that's yeah. So removing the points, or if you want to remove the entire diagnostic, you can click in the menu, just click and unclick by left and the right button, and you can remove the whole system. For example, the core tangentials system for CR, you can remove by a simple click.
So much.
Like this.
So 5 milliseconds is a really high frequency or a fast time step. And like, I thought they generate cakes every 100 milliseconds or so. So you're actually using GPR to basically, and
no,
how are you, because your data is not available at that interval either from most diagnostics, right?
No, most of the diagnostic data equilibrium is not at this fine time space, so it's just interpolating.
Okay.
If you want to use, you can use always EFIT03 if you want to have high time resolution equilibrium.
It's 20 milliseconds though for most of them, no?
No, the EFIT03 is at the time resolution of the Thomson diagnostic, so it's evaluated at the times when the Thomson data are available. And then this electron temperature working pretty well. The same is electron density, but in case of electron density, there are multiple options for the sources of data. There is sometimes scattering Larmor reflectometer, Larmor probes if they are safe. Also, reflectometer works only if there are data available. Or you can use even the CO2 interferometer. The whole Gaussian processes are natively trivially supports line integrity data. So we can mix the line integrity data with the local measurement, and it works really in the transparent way. So you have here the values from the CO2 interferometer, but it knows that these data are line integrated. It plots the measurements at the location where it's tangential, to which flux surface is tangential, but it will actually not fit this point. It will do actual tomographic reconstruction. Okay, and just wait, it's a bit more challenging, calculated, but it's also done in a few seconds. Yes, it's taking data. If you want to know how well are these points fitted, you can zoom it, and there is these error bars are the measurements, and little curls here is where the fit is. It's small, but usually you don't need to really know it. Yes, and now some more interesting features. In this discharge, there are large elms at the edge. See, and I can. It's not reproducing well the temporal evolution between elms. There is electron density which is jumping up and down, and the temporal evolution is not well reproduced. But there is, for example, option for this elm synchronization. I will select the time when the elms are roughly constant. Doesn't have to be exactly constant, but roughly like this. Select don't remove the points during the elms and use this elm synchronization. Fit, wait a few seconds, and yes, and you see that the temporal evolution during the elms is reproduced almost exactly. So here's the time slice, and you can yeah. So you see how well it is reproducing the elm crashes. It's useful for the transport analysis, for example, if you want to really resolve the temporal evolution between elms.
What algorithm is it using?
So it's using the Gaussian process, but I am introducing a correlation between the time slices, different time slices between the same elm phase. So by default, it's introducing the correlation between different time slices next to each other. But in this case, I'm also adding a discontinuity during the elm crash and the correlation between different time slices in the same phase. The same can be done also for sawtooth crashes. In the core, you have a large sawtooth crash. It's better actually visible for electron temperature. So extend the range. And you can here write some PT data signal, which has nice, like for example, ECE. It will try to estimate from this signal or the times when of the sawtooth crashes. Now fit. You see that it has tried to reproduce also the sawtooth crash in electron temperature. In this case, it's not doing the elm synchronization. It's not doing the sawtooth synchronization. It's only introducing the discontinuities in the time of the sawtooth crashes. So it assumes a small evolution in time, then a discontinuity, and then another small evolution and then discontinuity. And you can plot it as 3D plot if you want. Yes. And this tool is very well suitable for the transport analysis. That's why I built it. So for example, in case of you can load the Z-effective data, they are coming from visible branchdown. So all the measurements are line integrated. Just wait a few seconds, it will fetch them. Yeah, this is the radio profile. Some points, the blue points are coming from the Western array. The other points are coming from CR diagrams. CR diagrams also measures the physical branch. Now we just fit. Usually you need to check if there are some points, channels corrupted. In this discharge, there are none, but in many discharges, there are corrupted channels which need to be. And now you have, it looks like I see, but it's not that it is actual to reconstruction, but because the C-effective profile is almost exactly flat, it's very close to each other. It's almost fitting the line integrated data. And yes, it's also if you have multiple impurities in your discharge, it can work with it a bit much better, I believe, than OMFIT profiles. For example, this discharge 105.9, we had measured carbon, calcium, fluorine, oxygen. Carbon here. It is internally computing the carbon density from the measured CR intensity. Or you can, if you will turn off this option, it will use the data which are saved in the MDS plus. It can be different because it's using slightly different, it's using a different CR cross sections, and the option should be more accurate when you turn it on, usually. The same for here's the calcium. So we have done a laser beam injection of calcium, and you can see this jumps in the calcium density after each impurity injection. Yeah, so now the data are saved. I will fit it. Oh. Then you need to use the correct addition if there is multiple flavors of CR. Yeah, once they are done, you need to save the data from OneFit, and the data are saved in the same structure as the one from OneFit profile. So you have this fit object, where is the ion temperature. In this case, I have saved only the ion temperature, but I can do also electron density to have more. This was electron density. Save. Okay. The raw data are here. The raw data are used by some other modules like Improt as a source. The meta inside save more details if you want not just the fit, but also lower and upper uncertainty and lower upper uncertainty for the gradients. And it's also possible to turn on the option to save a random samples from the posterior. Oh yeah, I will have to finish soon. And here are several options for plotting. So just plot fit. It will plot the data saved in the MDS Plus or in the OMFit 3, which you have used for the fitting. So yeah, that's all that I wanted to show you. Do you have any other questions? Yes, please.
Hi. So do you have a plan to also include the feeding of like a fluid rotation profile in addition to the total rotation profile?
Fluid rotation is tricky. No, I'm not planning to do it soon. So I can, of course, load the fluid rotation from the database, but then you need to apply some atomic data corrections. I don't know how exactly do it, how to do it. In future, maybe, not now.
Yeah, it will be more like it's already cool enough, but if you also have like fluid rotation and the capability of like showing some ER profile in time, it'll be much like really cool.
Yes, I know. In future, I'm planning to do it. I have not done it yet.
How do you determine the timing for the Helm sync? Maybe I missed that.
Oh yes, there is next to this removing elms, there is the filter scope which is used. By default, it's using the filter scope, which is somewhere in pedestal 3 in MDS Plus, but you can use any other. Sometimes just try all different filter scope until it works. Yes.
One more question. So for here, like, what kind of procedure you are using for like boundary alignment with the profile?
When it saves the data into MDS Plus, yeah, the best option is to combine with kinetic eFit and use the QuickFit as a separatrix constraint, then run several times kinetic eFit until you have a self-consistent equilibrium. But else there is an option that it will align the pedestal to have electron temperature of about 80 electron volts on separatrix. It will use this value to align also electron density, and then align impurity density with this. By default, it's doing it. So there is use separatrix constraint, use impurity constraint. It's by default it's true. So the data which are saved in OneFit project are already aligned. Yes.
So this looks great for P3D where I can just load the data. What if I have a separate equilibrium and data in our space?
Yeah, so if you are running it from kinetic eFit time, it's using gequidisc files. So you can use gequidisc file, but a list of gequidisc files. It's not working with a single equilibrium, a single time slice. And it's working also on other machine, NSTX. It's working on ASDEX and CMOD.
So could we just replace the equilibrium contributor here with manually? And then do
Yeah, you can replace it with equidisc files.
Okay, thank you.
There's an online question.
Hi, Thomas. Yeah, I do have a question. I'm not sure whether I missed it or not. So is there any way that we can get rid of something like a bad note of the data that is clearly an outlier?
Oh, yes, of course. Yes. Just here's you press Control and
Mhm.
select the point, and they will be removed for the entire discharge. Or use the right mouse button and Control, and you will move them back.
Okay. Okay, thank you.
It's similar to GA profiles.
All right, thank you, Tomasz.